Okay, so I'm gonna go over like a setup, kind of skeletalized code setup for this homework, where we're asked to do condensation onto a random sphere. So essentially, we have a bunch of random walkers in the center. We have this absorbing sphere. If a random walker hits it, it gets absorbed. In the write-up, I talked about a cubicle simulation space, but let's do this again with the other option, which is spherical space. So here we go. Here. So we're going to have our absorbing sphere here in the center. We have to define our space. So we have some, obviously this has a radius of A, we call it. We have an outer radius here of R. And then I'm going to try to freehand a circle sphere here, a circle. And of course, all offside of it, that's fine. And then I suggested setting up a zone, an interior zone, something like this. Uh, which would be, say, R infinity, and where we have a pseudo-infinity zone where we recast walkers. So a random walker comes here, it gets absorbed. We can recast them into the zone. That way, we're always feeding random walkers in it and maintaining that this C infinity here, this concentration infinity, is basically essentially we're feeding for all time. Also, we talked about how to maybe probably use some kind of pre-arc boundary condition or maybe just recast again into this pseudo-infinity zone if a walker walks off our space. So we recast it, say, over here, or maybe we could just randomly put it in our infinity zone. So instead of coming over here, you say, oh, it doesn't really matter as long as it's just born again in our pseudo-infinity zone. Here's a code template here. We've seen this before with random walkers before. Just let's begin here and just start defining some things that we need. So we have our seed for our random numbers. We have the number of walkers we're going to have. We're probably going to want to do at least 1,000,000, I think. Depends on your space. How many time steps we're going to keep going. Say 100, doesn't matter. What are other things we need to do? Well, we need to define our simulation space. So we need the outer radius. So that's just going to be another definition. Oh, dang it. And whatever should it be? Let's do 10. Well, no, this is the outer space. Let's do the bigger the better, in theory. We need to define our pseudo-infinity zone. Again, these are things you can play with. Let's do 99% of R. And inner radius, the radius of our absorber. A. 10. Right, these are things we need, constants we'll need throughout. So we're going to have to initialize our random walkers. So let's go ahead. And first we need to put them in space, some kind of space. What do we need? Well, we're going to need some arrays. Do an X, Y, Z array for the coordinates. And I want to allocate memory in 0 amount. So we're familiar with this before. Allocating here, I'm gonna make a function that zeros an array or assigns a value to array. So I should start defining my functions before my definitions. There's one, and I've already coded this beforehand. It's a simple little function. Okay. Let's build. Oh, easy. Okay. What else do we need? We need to initialize. So I'm going to have a function that does initialization, which means essentially placing all our random guys. So I'll need a function that does that. Void initialize void function. And it's going to take in our three integers, our three arrays, not our integers, three arrays for our coordinates. So it's going to find the initial coordinates. And then let's work a little bit on how that would actually look. So essentially, since I'm going to use my seed here, and we're going to, I should initiate my first thing over here. We should probably, before we initialize our random numbers, we need to initialize, or initialize the system, we need to initialize our random numbers. So what are the rules here? We need to place them randomly between R and A. And we've already had it, so that'll evolve since it's spherical space, spherical coordinates. How do we go about that? Well, we know how to do spherical coordinates when we're just looking at angular. But let's go back to our differential element here. So we want to do uniformly. So dv in spherical coordinates is r squared sine theta dr d theta d phi d theta. So essentially, if I want to say the probability of filling a volume is equal to this uniformly, it's just equal to dv. More accurate, let's say, is the probability of filling a volume per volume equally should just be 1 or a constant, right, times this, right? We're going to fill it evenly. So that's what we're going to do here. So you have to see here that, okay, as we said before, the probability of filling our theta is because it's just going to be equal the probability of filling theta, the probability, or d theta, times the probability phi, d phi, times the probability of r, dr. So I want to fill this volume evenly, constant dv, right, probability dv, is equal this, and then we can just say say match this over here with this. So the probability d theta, we've already went that before that sine theta d theta, or it's d cosine theta. The probability of phi d phi, right, it's going to be just d phi, or 1 d phi. And that means our probability of finding r is going to relate to r squared dr. So you're going to integrate that and find your CDF. Your radius goes as cubic, so that should give you a hint on how to randomly select a radius to put your initial monitor. So let's go back to this example here. Let's erase all this. Why do we need to be selective here? Right, so we can see that our CDF is going to be related to the radius to the third. Or our random number, so our R is going to be our CDF to the third. Why is that? Okay, let's go back here. Let's make our sphere. So we're starting from the center, right? So if we had it uniformed, it's just as likely here as here as here as here. So if it's most likely here, let's just do, okay, same, we're going to select with the same R and then just fill radially at different angles. I'm going to say you have a lot of density here and low density here. That's why you have to have sample our random numbers from 0, 1. Has to go our radius to the 1/3 has that 1/3 power. So our random radius, our radius equals our CDF, which goes from 0 to 1, we'll call it Y, to 1/3. And then also you have to say, hey, if it's in the, you have to wait to prevent the random walkers to being ported or teleported immediately into the absorbing sphere. You don't want that. So we have our initialization here. We'll go ahead and just build that, call that immediately in our main here. I'll leave the programming of that to you, however you want to do it. And its inputs are just going to be our X, Y, Z. And then we need to go from the for loops for our time, and so T for time, and our different walkers. So for T equals 0, T is less than, what do I call it in here? In time. And then, of course, in that loop, we have our spatial loop. All our random walkers are going to move. And there's going to be some stuff here. So, other variables, we need the current. Current is called I, right? So that we need to know the current for each time step. So at each time step, before we move, we're going to set I 0, and then you're going to have some mechanism to count how many collisions there are per time step with the absorbing sphere. So what do we have to do here? What are the steps here? Well, we have to move the walker. Okay, and then after we move it, what do we have to do? We have to check if it hit the center sphere. Okay. And if that happens, well, then that means current when it goes up. And we have to recast that walker. Right? So we move the walker, that's the first step. Or I can say 1. No, that should be inside the column. So 1, 2, check if the walker hit the center, and then 2A, you have to walk, if it does happen, you recast, and increment I. Also, what do you have to do? If not, check. You have to check to make sure the walker is still in the simulation space. Right? Because you make this check. If it hit the absorbent sphere, you go and you recast it. You don't have to do this check. So if, there's no reason to do this check if this happens. So this is why this is like 2B. This is another, so it's if either this happened or nothing happened. It's just safe. So you have to make this check. If this check runs true, then you don't have to make this check. But if this check runs false, it didn't hit the absorbent itself, you still have to make this check. So that's why it's indented here. And if that happens, okay, you can use the periodic boundary conditions to, or you could just recast the walker into the pseudo-infinity zone. And you just keep doing that. And then ever so often, you record your concentration. Okay. So, let's see. I think this, I'll let you guys, this is the meat and potatoes here. I'll let you guys work with this. Let's talk about, well, record CFR. We did the video on making a histogram. That will be very useful here. Obviously, that's going to input the coordinates of your walkers because you have to find their radius. Or you could even make a third array that just holds the radius, is how far they are from the center, and just put that in there. That might even be helpful. It's up to you. But you would want to have several of these recorded per simulation. You don't just want to have it go and do the end time. We need to have something available so we can make several files that have different names, like concentration at time blank, concentration at time blank. So we're going to modify now our print array function that I've seen a lot of people have been using. So we'll go over that right now, how to do that. So a lot of people have been using this like print double array, print in array. We're going to use the print double array, and I have added something, this buffer here. Basically, it's a string. This is an array of characters, and we're going to use that here. So I'm going to go ahead and just make this as a variable. And then I'm just going to copy and paste the code directly from this other code where I've been using it. And it's very similar to the print array that we've been using. The only thing different now is it's going to take a file name that we give it, and when it opens the use the fopen, it doesn't. This isn't. See, this isn't quotes. It's taking the actual words, the actual characters here, and placing them right there. So that way we can import any name we want as a character buffer, as a character array, called buffer in this case. And now it's so this would be where you would write your concentration per R. Gotta remember your semicolons. So how would we actually use that? Let's see. 50, right? We're not going to make anything that's more than 50 characters, let's say. Or 100. Unreferenced fopen. Oh, I'm getting this stupid warning. Ignore this warning. Well, let's just fix it now. So good to go over these things more than once. So remember, you go to C, C++ in your project options, pre-processing, you go here, edit all the way to the bottom of the list, and enter that, what it says there in the one thing. It's kind of annoying to do, but only have to do it once per project. Okay, it's just giving a warning we haven't defined that. So how would I print my CR? This is going to be a vector, right? I'm going to have some vector where I hold that concentration. So I might even define a DR here. I'm going to give it a length. So let's do that here. So we define a DR. This is for, and we'll call that to 1 right now, right? So our shells that we're finding our concentration are going to be 1. And then I can define, or a constant integer. It's going to be, which equals, call it length. It's going to equal R divided by dr. And then I can make another double. It's going to hold my concentration. So that's where I'm going to put my concentration profile. Every so often, I need to store that and put it to a file. And of course, we need to 0 it. And this is why I like this little, here I can just put any, I can initialize any array to any value. So this is the array, the value it takes, and then the length of the array. Helpful little set of helpful little sub-function or subroutine or function to have. Okay, so back to this. And using this print double array with this new buffer. So I'm going to introduce a new built-in function to see. So this is where we give. It's going to be the sprintf. sprintf. That's going to take, and it's just like any other, like the fprintf, but it's going to put it into a character. So instead of a file, we're not printing to a file, we're printing to a character, array of characters, called our buffer. But it's the same way of the fprintf. And then we can say if this is C R at and then give it a time. Control %D. And you could even give it an extension, make it a text file. And then what do we call that? That's we're going to give it the variable t. So now it filled this character array with these characters here, and it replaced this %d with t. So if I do this at every time step, it'll have concentration at time 0, 1, 2, 3, all those files. And then we can just call this. So our print, we're going to give it our array C. The size of the array is the length we define as a constant integer. And the name is just the variable buffer. So this actually is how we're going to record, but before we record, we have to find C of R, the concentration, radially. So find it, you record it, this is how you record it. There's the function, obviously the build. So here's a good skeleton for your code, your concentration code. Obviously there's a lot of functions I left out. You need to have code to move the walker. You need to have the code to check if you hit that center. You have to have a code to recast the walker in your pseudo-infinity zone. You need code to either do recast, or you can use the periodic boundary condition, so you can do that. You need code to find the concentration radially, things of that nature. But I think this gives you a good starting point. I'll post this file with this, plus along with this video. But let's go through it one more time, see what we're doing in our main. So finding all our variables, because we have a lot of walkers, millions and millions of walkers, right, in this space. Zero out all the relevant arrays. I have my concentration that's just that goes out radially. I'm going to measure concentration radially. So it has a length that I define. So you can zero it out, initialize my random number, initialize the positions of my walkers. This is my time loop. So I go through time here, and then this loop here just moves the random walkers and does all the recording. So this is current, how many things hit my absorbing stator for time step. Here's where it gets in. So if something hits it, it gets incremented, resets to 0. So you're going to have to keep track of this current per time. That might be a different file, or you just put that into a different array. So this is not a complete. You're going to have to add to this. Also, this whole notion of C infinity, right? So everything, the space is filled with C infinity. Well, if that C infinity is just defined as how many walkers are per volume of simulation space. So you can define that. So you should know that. You should be able to calculate that easily. That brings us about a half an hour. I think we're going to leave it there. If you have any questions, please let me know. Email me, ask in my office, and I'll see you Tuesday.